Gia. All right. Um, so yesterday I gave you some uh, very fast overview of how the instruments work, what the nature of gravitational waves are and their sources, and then I hope I set it up so that you appreciate the complexity of the instrument and how it's important to understand it before we go and try to extract information about science from the data. Okay, so today I'm going to focus, I'm going to zoom in on that, okay, and try to understand how all the complexity of the instrument manifests itself in the data, in particular in the noise that will plague our measurements, okay? Once we understand that, we can move on to try to do science with the signals that are hopefully present in the data. Okay, so at the end of last lecture yesterday, we saw that in the end, these instruments produce a huge amount of data, 200,000 channels monitoring everything having to do with the status of the instrument and its environment at any given time. But the real goal here is to produce this one data stream called the differential arm channel that is then turned into a calibrated strain, which represents the changing length, the relative changing length between the two arms over the length as a function of time. And that you can write as this channel, so it's a time series. As we'll see, it's sampled at 16 kilohertz, so we have a data point of 16,000 data points per second, okay? And that will have a component coming from the strain produced by any passing gravitational wave that may be going through, projected onto the detector via the corresponding antenna patterns that we that encode the angular sensitivity and the geometric properties of the instrument, and there will be a huge component from the noise caused by the functioning of the interferometer and what's going on around it. So again, just to remind you, the signal that a given interferometer sees, it's a projection of the strain tensor of the gravitational wave onto the detector via these antenna patterns F plus and F cross that are a function, you can think of as a function of the sky location and orientation of the source. And then those get multiplied by these polarizations, H plus, H cross, that come in, they give you the amplitude and phase evolution of the signal that is determined by the source only, and that's what we call the waveform. But this will be what we will focus on for the rest of the lectures. Today, we're going to dive in on the properties of the instrumental noise and the key features that you need to understand before you make any statements about science based on LIGO or Virgo data. Now, before I actually do that, I'd like to come back to a point that I think was kind of confused, or I kind of, a lot of people ask me questions about this issue of the polarizations and how the detectors see them. And so let me revisit this a little bit. So as I showed you last time, there's some characteristic sensitivity pattern to gravitational waves coming from different locations in the sky for a given instrument that if you imagine you sit in the frame of the interferometer and you have the arms along the black lines, then these kinds of plots show you the sensitivity, the radial distance represents the sensitivity, so how much the instrument responds to a gravitational wave of this given polarization coming from that given direction with respect to the instrument. Okay, and so I showed you these two plots that correspond to the plus and cross polarizations defined in some specific frame. We many times, because an arbitrary gravitational wave, we have, in general, if it's what we call circularly polarized, by definition means it has equal components of both, right? Just like circularly polarized light means you have equal components of vertical and horizontally polarized light. Here, circularly polarized gravitational waves means you have components equal amounts, roughly, of both polarizations. So when we're trying to determine what the sensitivity of the overall sensitivity of a given instrument is to gravitational waves, regardless of polarization, we sometimes show this peanut here, which really corresponds to just the quadrature addition of the two polarizations. Because any arbitrary any arbitrary signal will have these two components, and so in general, the overall sensitivity of an instrument to a gravitational wave that's arbitrarily polarized will be given by this peanut here, which we call the tensor, overall tensor response. Tensor just means that it's just both plus and cross in this particular context. Okay, that comes because in other beyond GR, you can have other polarizations that are non-tensor, but don't worry about that. So you see, here it's clear that the instruments are largely omnidirectional. Okay, they detect signals from any direction, roughly, except for these very specific blind spots. Okay, so if the source has to be very particularly aligned so that we don't see it at all. Of course, the sensitivity is largest when the gravitational wave is coming straight from above or below, because the projection of the strain will be maximal along the plane of the interferometer, and not so much if it comes from the side. But we still have sensitivity all around. Okay, so how does this work when we have a network of detectors? Imagine, well, take the Earth, and you have a lot of money, so you can place a bunch of interferometers around the world. Each of them, 1, 2, and 3, has its own detector tensor, so it's defined by the orientation of these arms in space, right? So you have 6 vectors here defining each of the arms of each of the instruments, and you can construct these geometrical objects that, as you recall from last time, give you the differential arm measurement that each of these instruments is making. Okay, then you have a gravitational wave that comes from space somewhere, okay, and that is characterized by its own tensor that describes the stretching and squeezing along these characteristic lines. And this you can decompose into the 2 polarizations, as I showed last time. So the gravitational wave goes through the Earth, and it will ring up the different instruments, but the response in each of the instruments will be slightly different because each of them is taking a different projection of this original geometrical strain object, okay? So the signal you see, although it comes from the same gravitational wave, it'll have different amplitude and phase just because you're looking at different components of it, right? So you get 3 different sort of signals, but they all correspond to the same gravitational wave. Because we know what this detector is for each of them, then we can backtrack what the original geometry of the gravitational wave was if we have these different measurements from the output of each of the detectors. Does this make sense? Right, and so these wiggles just represent a function of time, right? Because each HAB is really HAB of t. So at any given time, it's stretching and squeezing the arms of the interferometer. Okay, so this information is important because the amplitude and phase and timing of the signals of the different instruments allows us to reconstruct the sky location and orientation of the source, right? If we have a specific model for how those get sourced. In particular, if you can imagine that a lot of that comes from not just the polarization, but the timing between the instruments, as I mentioned. You know, the gravitational waves travel at the speed of light, so we can triangulate where the signal's coming from. So this is for, I think this is for 150914, where we only had 2 detectors, and so just based on the delay between the signal seen in one instrument and the other, you can locate the signal to some ring in the sky. So this kind of plot represents the sky, and then the orange, the dark part, represents where we believe is most likely that the source lied. And so in general, you would have a circle in the sky that corresponds to the equal delay between the 2 instruments. And then you can discard some of that based on the polarization information, and you get this wedge here, okay? And you're doing that by knowing that the waves travel at the speed of light, by knowing that they are composed of plus and cross polarizations, and knowing the given orientation of the instruments at that time where the signal arrived. Okay, so I made the statement last time that the 2 LIGO instruments are co-aligned, or actually anti-aligned, and so they measure the same polarization. So I wanted to clarify what that means. It's simply just a fact that literally if you parallel transport the two instruments on the surface of the Earth, you would find, and you can go to Google Maps and do this yourself, right, that you'll see that one of the LIGO instruments in Hanford is oriented something like this with respect to the local north, while Livingston is oriented in the flipped way, right? So a gravitational wave that comes in this direction will actually affect both instruments the same way, except with a flip sign. And so that just means that the response of the detectors will be the same, except for a minus sign, roughly speaking. This is not exactly true, but that's roughly true. Okay, so the signal seen by the two instruments will, so let's say the Hanford instrument and the Livingston instrument will differ by a minus sign, so it will be flipped in phase, and there will be some delay because the instruments are far apart, and so depending on where the signal came from, it will hit one of the instruments first than the other, and this delay can be up to 10 milliseconds, which will correspond to the gravitational wave coming from directly aligned with the line defined by the two detectors. And that's just the distance between them translated into light travel time. For 15 and 14, this was something like 7 milliseconds because it didn't really come from that direction exactly. Okay, so just visually, you will get some strain at the two detectors as a function of time, and then you will see, if you just look at it, that they basically look the same, except one of them is flipped, so you can flip it and time shift it, and then basically you'll get the same waveform, the same output in both. But this is just it's just because of the fact that the two instruments are anti-aligned. It needn't be. And if you looked at what Virgo would see, for example, it would have a different morphology here, and this will no longer be true. So the instruments, the LIGO instruments, are measuring a specific projection, the same essential projection of the gravitational wave, and so that's what I meant by measures one polarization. Yeah, so that's a good question. We were discussing that yesterday. So this was a design choice that was made back when the instruments were designed early on, and it was intended to maximize the similarity between the outputs of the detectors on purpose, so that it would be easier in a sense to make sure that the detection was real, right? Because as we will see, we rely on having coincident and coherent signals across several detectors to make sure that what we're seeing is a true astrophysical signal, not just some random fluctuation of noise in the instrument. And so back then, it was decided that it was more important to make sure that we could maximize this data being as similar as possible, so there could be less doubt that the candidate gravitational wave was real, at the expense of losing polarization information. So it was just that there was a trade-off there. I'm not sure how it will be aligned, but I do know that it will improve our sky localization ability dramatically. Okay. Yeah, I don't know exactly if it's already been decided even how exactly it's going to be aligned or not. I'm not sure. Yeah, there's no choice between aligned and anti-aligned. There's a choice between any angles, right? You can only speak of aligned and anti-aligned. I guess these detectors are closed, and it makes sense, right? Otherwise, you have to take into account the curve. I don't know where it lies on the surface of the Earth, but yeah, you have many choices. I mean, ideally, we would have a bunch of detectors oriented all in different ways, and each of them measures a different projection of the gravitational wave, and we can reconstruct uniquely what goes on in that H tensor. We don't need that many. I think there are studies. I'll come back to this, maybe the lecture tomorrow or the one after. But studies show that after you have 3 or 4 detectors, then the improvements are marginal. In terms of just, then you still get improvements because not all the detectors work all the time. So you still want more detectors because sometimes one is down, and so you still need a network. But in terms of localizing, yeah. Okay, so actually I have a plot for this sort of, just to visualize how having more detectors help. So this is for the 170814 signal, which was a binary black hole merger. And so which was the first one that we detected with 3 instruments, by the way. And so you can see that, well, in blue, you have the sky reconstruction, so what we estimate to be the most likely sky location of the source, if we just use the data from the LIGO instruments, Hanford and Livingston. Okay, so you see it's this, again, it's this piece of this big circle, gray circle in the sky. And so this gray circle here just indicates points that in the sky that will give you a specific delay between the two LIGO instruments, okay? The one that was observed for the signal. I don't remember what it was, right? But if you have 2 instruments and you know that the signal arrived with some delta t between them, that defines some region in the sky, which is a ring, from where it's a locus in geometrical parlor, on the sphere where that source could have lied so that the delay was whatever it was. And that's what this ring is, okay? If you have 3 detectors, you can define 3 such rings. And so, because there's 3 pairs of detectors that you can define. And that's what the other rings are. It's just Hanford and Virgo and Livingston and Virgo. And then the source must have come from where they all intersect. And that's where the green contour, what it's defined. So essentially, that's what's going on. I mean, we don't do it like by hand, right? We have, as we'll see, we have inference code that does this automatically. But essentially, the geometry is pretty straightforward. And so you see we can improve the sky location dramatically by having 1 extra detector. In particular, because essentially the LIGO detectors work as 1 detector in terms of polarization. Okay, and this is very important for astronomers that want to actually point their telescopes to where the source may be. That was a sort of detour. I wanted to clarify this because I realized it might have not been super clear, but it's important. Are there questions before I move on to tackle the noise? Yeah, so the gray ring is just timing information, but we also have some polarization information, although imperfect. And I believe that's the main reason why you get half of the ring rather than the full ring. Yeah, the polarization information comes in here because the response is different. The response, so this is a linear combination of a response to the cross and plus components of the signal. And the sky sensitivity of those is different. And so you get some extra information, if that makes sense. So you have to simultaneously reconstruct both the polarizations and, well, we have to go through this again. The source location and the polarization simultaneously. We'll see how we do that later. It has to be self-consistent. Any other questions? Okay. So now I would like to discuss the nature of what the detector actually puts out, in particular how we go from some voltage in a photodiode to a quantity that represents the strain, so the dimensionless change of length over length in the arms. Joe will cover the details of how of this process, which is called calibration, right? It means how do you take this physical thing and make it turn it into the quantity in absolute terms that you want scientifically. So I'll just, and I'm not an expert in this, so I'll just brush over this, but it's important that you understand that we can't just look at the detector and tell what's going on. It's a complicated process. Okay, so the question is how to translate the measurement that we make at the photodetector. So if you at the photodiode, so if you remember, we have this complicated optical system, and then in the end we have a sensor that's basically measuring a power or a number of photons that come out of the dark port of the instrument, and that's somehow related to the changing length, the relative changing length of the two arms. But how do you actually make that connection properly so you get the strain value correctly? These machines are extremely complicated, and it's not straightforward to actually say how that happens. So calibration is a complex and quite interesting process, but the bottom line is that to actually know what your instrument is doing, you have to put a known input, look at the output, and then renormalize, if you wish. And so then you know, if you know what kind of strain you're putting in, so you push the mirrors a little bit by an amount that you know very well, and then you look at what the output it is that your instrument is giving you, and then you can say, okay, this output corresponds to this much changing length over length, and so on. It would be, in an ideal world, we would have our own sources of gravitational waves. We would put them right over the instrument, go around, we know exactly what the strain is, we look at the output, and we can tell exactly, this much voltage, this much strain, because we know exactly what that is. We cannot make our own gravitational waves for reasons I hope you appreciate. But what we can do is to just push the mirrors, okay? And we can do so using radiation pressure. So we have a system of auxiliary lasers called Pical lasers for photon calibrators. So these are different from the main lasers of interferometers that I discussed last time. Their sole purpose is to push the mirrors. So we use photons to push the mirrors by a little bit that we know very precisely. Okay, so just keep in mind how crazy this is. We're so sensitive that we can just shine photons in a very precise way and know exactly what the minuscule displacement that will cause, and then look at that in the output of the readout, and then use that to associate that number, digital count, to some strain. So we essentially push the mirrors with light to actually know how to interpret the output of a detector. Again, the reality is way more complicated, like everything in LIGO. Everything I tell you is a fiction, okay? Everything's way more complicated, and there's infinite levels of engineering complexity to this, and I hope Joe illuminates some of this a bit further, but actually doing this requires a very detailed model how the interferometer and all its parts are working together, and it's run in a live manner in our computers that actually are actuating and interacting with the instrument in a live and complicated way. But anyways, the basic idea is this. We have these mirrors where you can imagine this is basically the mirror at the end of the arms. This is the interferometer laser beam, the main infrared light that we use for the differential arm measurement. And then we have these auxiliary lasers that hit the mirrors at different locations and drive them at specific frequencies that we know. For example, there's some here with around 23 hertz and around 300 and 1,000. Okay, I don't remember. They are different from the interferometer, different instruments, and they change. But you see, we drive them at a particular frequency quite loud above the noise floor, so a signal-to-noise ratio of 100, and then we can, in a live manner, gauge what the response of the instrument is to this known input. Then we can remove this, since so too, we remove these lines then from the data so that they don't bother us. Yeah, the calibration is done in two stages. There's one of them that's low latency calibration that is actually built into the functioning of the instruments. The same computers that control that run the control loops and all that have the calibration, and this whole sensing system has the first That's the first stage of calibration, and it reports on that. Then, because it's low latency, there's limitations to it that Joe will be able to explain, and so then it's revisited offline once the data run has been done and adjusted to be more precise. And this is important, as I'll come back later, because this means that we have different versions of data. So when you read our papers and we publish a new discovery and we make some statements about the properties of the source or whatnot, then that's all contingent on the best available data at that time. At a later time, we'll have better data available among other reasons, because we will have understood better the behavior of the instrument at that time, and we can recalibrate the strain that we obtain, and that will change the results of the science sometimes. In general, not to a huge degree, but sometimes to a measurable degree. And so when you read our papers and you work with our data, you need to understand that things fluctuate and things change as we understand the data better. And this is one of the reasons. And you see that there's scientific statements that change because the calibration changed. And so then something we thought was true is no longer true. And you need to understand that that's just the nature of the beast, okay? It's not that we're doing something wrong. It's we're doing things better. And so we have different versions of the data. Okay, so some points to keep in mind. The calibration of the instrument is time dependent because the instrument, as I mentioned, is a very complex machine. As any of the optical parameters or whatever alignment of things in the instrument changes, its response changes, so the output for any given actual strain will be different. So it's slowly varying, but when we calibrate it, that's why it's done live, because it's changing. It's not like you can calibrate it once and you're done. It's frequency dependent because the instrument responds differently to different frequencies, right? The whole sensing system, how we read out, how displacements gets transduced into a digital signal depends on what frequency, how quickly those displacements are happening. So our calibration will depend on the frequency, and we'll have better calibration at different frequencies. For example, we don't have any calibration that can be trusted below 10 hertz because no one has computed that. It's not useful. Or like above like 5 kilohertz, I think. The calibration is imperfect because it depends on our knowledge of the instrument at any given time, which is necessarily contingent. It will change as we understand it better. We can know it infinitely well, but we can get to know it better. So it's improvable, not improbable, but improvable. Okay, so as we improve our understanding, we can also improve the calibration, which leads to different versions of the data that allows us to do better science. So this you need to understand. Luckily, the calibration is imperfect, but we have ways of estimating how well we know it at any given frequency. And this is what we call the calibration uncertainty budget, which is a way of estimating how well, so if I give you a data series that says this is a strain as a function of time, then we know that there's some error in that because of the calibration. We don't know perfectly what it was at that time, given the output of the detector. We have done our best to make that representation be as faithful as the actual strain, but there's some uncertainty there. And so we quantify the uncertainty in the calibration in terms of the amplitude at a given frequency and the phase. That's what you see up here, amplitude, and down here, phase. So this is a percentage in amplitude. So for example, 50 hertz, we know the calibration pretty well to less than 2.5, between 3%. And so when you are doing data analysis, you have to take into account that we know the value of any given of the amplitude at this frequency only up to 3%. So you should take that into account in the uncertainty of your measurement. Then for the phase, so this is in the Fourier domain, so it's an amplitude and a phase. Then we know the phase to a few radians. Well, depends. You see that at higher frequencies it gets harder, and we have more uncertainty in both the amplitude and the phase. The phase is generally more important than the amplitude, but it depends what kind of science you want to do. Anyways, this gets improved, and it's improving constantly. We have a whole team of people that work on calibrating and understanding the instruments better, so this uncertainty gets narrower and narrower. It's not the dominating factor in our measurements at the moment. At some point, in principle, this will be a limitation on how well we can measure gravitational waves, right? Because you're limited by how well you know what you're reading out. But it's not, at the moment, there are other sources of uncertainty. This is for the Hanford instrument in the second observing run. So it's cumulative over the whole several months of or I don't know how long it was, I don't remember, of observation, of 1 month, I guess. But it's actually computed every hour to represent that time variance. And then for Livingston, it looks qualitatively the same, but actually different in the details. This is what we as data analysts downstream take and then marginalize over and fold into the analysis. So all the parameter estimation that we do, which I will explain tomorrow. So when we let's say, we saw 150914 and we want to measure what the black hole masses were of the source that caused that signal. We have to take into account that we don't know the strain to infinite precision. And so these errors get folded in, and so when we tell you we saw the binary system had a total mass of 70 plus minus whatever it is, 10 solar masses, in that 10 error, there's already folded in these calibration errors. And you have to do it, and you have to, if you analyze the data, you have to be aware that you should be doing that as well. Yes. I'm sure the answer is yes. It doesn't have to do with the actual noise, but the sensing and how accurately you know the output. You know, even if it's not about how much noise there is. Even if there was no noise, we would still not know the calibration that well at those high frequencies, just because it has to do with the latency of the sensing function. But that's a question that you should ask Joe. Any other questions about this? Yeah. Up to, yeah. Yeah, so if you look at this, so this is an example. I think there's usually at any given time at least 3 calibration lines for any instrument. You see we have one at like 10, 20 hertz, 300, 1,000, and we move these around. But yeah, we can drive it at higher frequencies also. And I should say there are a lot of other pieces, moving pieces that go into performing this that, again, you should ask Joe. We don't just swipe with the laser through all the frequencies. We have some model of how the instrument works, and so just knowing it at some frequencies allows us to model the whole thing. Yeah. Yeah, well, I won't talk about how this budget is produced. Maybe I misspelled archive. Maybe Joe will. This plot was produced by my former roommate, so I know that it is done by a Gaussian process regression. So, I mean, so to interpret this, you need to, so the data have already been calibrated to the best of our understanding, and this is a measurement of how certain we are that that was done correctly. So this itself has a model of how the calibration works built into it with all these parameters that are time varying and frequency dependent, and then you're using splines to model this error in some way that is detailed in this paper. I won't go into details into how this is produced, but all we need to fold into the Bayesian analysis of the parameters are these frequency dependent curves, which are basically a frequency-dependent uncertainty in amplitude and phase, and then we marginalize over those. So this is sort of a product that we then plug into the inference stage. That I'll describe that part tomorrow. Does this make sense? All right. So now we, after this whole involved process, we can actually have a time series that, as I mentioned, is sampled at 16 kilohertz that represents the actual dimensionless strain in the arms at any given time. So the relative changing length of the arms at any given time. So it's at 16 times, 1,000 times per second. So then you're all happy, and then you download the data, and you look at a time around 150914, and you find this. And you say, well, my friends told me that 150914 was so loud, I should just see it by eye. And yet, it's just whatever. What is that? All right, so this is actual data for the Livingston detector for time around 150914, our first detection. And you'll see that after you've calibrated your instrument and done all that, that's just the beginning of the data analysis process. Okay, just by looking at the data, you can't do much. So, and then I should say, we actually sample at a multiple of 2. So it's not 16 kilohertz exactly, it's 16 whatever, 384. So before, to understand everything about data analysis, you need to be very solid on Fourier analysis of data. So maybe this is all news to you, but we have to make sure that we're all on the same page, so we'll brush over this. So we start with a time series, and we know that any time series can be represented, or any series of data can be represented in a time or frequency domain representation. These are just two bases to represent the same object in a function space. So for those of you who are mathematically inclined, if you have a continuous signal that lives in L2, which means square integrable functions over some period, if you're speaking of discretely sampled series like we have in LIGO, we don't have a continuous thing, we have something that's discretely sampled, then it's the space of square integrable sequences. But it doesn't matter. The point is that you can, if you give me a data series that's a function of time and sample at some discrete time interval, I can change my perspective, change my basis, and represent that same information in terms of frequency Fourier components. And you're effectively just doing a Fourier transform, which would be very familiar to any physicist, except you're probably doing it digitally in the discrete version, which I've written here. So you start with a time series x, and you end up with x tilde, and that's just a Fourier transform done with a sum instead of an integral. Yeah, so we will have a sampling rate, sampling interval delta t. So this is in the case of LIGO, the raw data, it's 1/16 kilohertz, and then we observe for some finite time t, that's n, the number of samples times that sampling rate. This is, you've all seen some of the version of this before, right? Okay, so what other things you need to keep in mind is that if you observe a signal for a period of 1/t, then you can resolve its frequency components with a resolution that's given by 1/t, right? So if I observe for 100 seconds, then I can distinguish frequencies in bins that are 1/100, so 0.001 hertz in width, and this is your resolution for the frequency components. You can get an intuition for that because that's the slowest sinusoid basically that you can see oscillating in a time t, and that this will be the slowest frequency unit that you can resolve. So that would be your frequency resolution. Then if you sample your time series at a time delta t, then you will be limited in the kinds of signals that you can resolve, and there'll be an intrinsic frequency band that you can detect. So you can't detect infinitely high frequency signals because you're only sampling at some given rate. And this highest frequency that you can see is called the Nyquist frequency, named after someone long time ago. And what that is really, it's just half of the sampling frequency. okay? And you can see that that's the case just by considering a sinusoid and then imagining that you sample at a very slow rate, so you only get data points every so often. Let's say this is time, and so every time delta t that's long compared to the period of the signal, then you might just get data points that do not represent the oscillatory behavior. So you cannot reconstruct the ups and downs of this signal just from the red data points, right? You're just not sampling with enough resolution to resolve this change. If you sample at a higher rate, then you can actually start reconstructing this oscillatory behavior, and so this is where this cutoff comes from. So if you start with a continuous signal that has components between some frequencies between 0 and some maximum frequency, then you must sample that continuous signal at least this rate, determined by the Nyquist frequency, which is the maximum frequency you want to allow. If you don't do that, what you get is called aliasing, because then the power that's in these higher frequencies will appear in your data as power in lower frequencies. So it's like an alias, okay? So for example, let's see. So here you see we have, in this case, we have a sinusoid that's evolving, that has a long period, and we're sampling it at intervals marked by the circles, and this is fine. So this is enough sampling that we can reconstruct the signal well. But if the signal had a higher frequency, then we would be missing, the ups and downs in betweens, and we would be sampling this way. And these two signals are basically so this higher frequency yellow sinusoid will look the same as this lower frequency blue sinusoid. And so you won't be able to distinguish it, and it will look like you have a large amplitude at this lower frequency, where in reality what's happening is that you're not resolving this higher frequency component in your signal. That happens when you sample not just in time, but also spatially. So if you look at this picture that I stole from Wikipedia, then you'll see that the bricks here have some intrinsic pattern that has some characteristic frequency in space, okay? So some space in between them. And if the resolution of the image is not high enough to satisfy this Nyquist requirement, then you'll get these patterns appearing because it looks like this high frequency stuff in the spatial distribution will appear as power at lower frequencies, and you get these rings and one weird features. This is bad, okay? You will be mischaracterizing the content of your data if you do this. So bad, okay? Make sure you understand what the frequency content of your data is before you do anything. All right, we have fast algorithms to compute the discrete Fourier transform. I should have called this a discrete Fourier transform, and then the fast Fourier transform is just an algorithm that very efficiently computes that. So you don't actually have to do that sum I showed earlier by hand, which is computationally expensive. You can do NumPy or SciPy, FFT, and it will very fast, very efficiently compute the discrete Fourier transform of your signal. But there are some things to bear in mind. When you compute a discrete Fourier transform, there's an implicit assumption of cyclic boundary conditions. This means that in real life, we never have an infinite sampling of our signal. We only have some chunk, right? We'll only observe from some time t. So imagine if this was actually a sinusoid that extended forever, we only observe it for this short window of time. When you take a produce a DFT by an FFT or whatever analytical, but whatever way you want to compute it, the mathematical construction assumes that that's just a sample that repeats infinitely. Okay, so if you are not worried, if you're not careful, you will implicitly have these discontinuities in your series, right? Because it's assuming that it repeats itself as it appears. So you will have these jumps, and this will result in in the frequency domain representation of this, having high frequency components to resolve this sort of sharp feature, which then will get aliased and show up as lower frequency stuff, and it will mess up your Fourier transform and will also be bad, okay? That's called spectral leakage. So whenever you take a Fourier transform in our world, because you have to worry about well, in any case, but in other applications, this doesn't come up as often. So in cosmology, when you're working with the CMB or something, you naturally have cyclic conditions because your data is defined on a sphere. For us, that's not the case. So you have to make sure that you're properly windowing the data, and windowing is a process where if I have some data that look like this, then I can multiply it by, in this case, it's called a Tucky window, but it doesn't matter. It's a function that ramps up to 1 and then goes back to 0, so that you actually make this look cyclic. And then, you know, the algorithm will assume that this repeats over and over, but it won't corrupt the data in the same way. It will alter the frequency content in some sense. It will affect frequencies. So if this ramp up has a characteristic time t, it will sort of affect frequencies that are below 1 over t, if that makes sense. But then if you're only interested for higher frequencies, we've been sensitive to this modification that you did, and so you don't have. That's what you want to do. You would want to avoid these spectral leakage issues and rather control the transition from the time domain to the Fourier domain. This is boring but extremely important, because people, if you're not aware of this, you will download our data, you will do stuff like this, and it will look like there's all sorts of signals and weird things in our data, and it's just that you're not properly handling these transformations. And this has happened. Okay, people writing papers, and it's wrong. Well, it depends what you're doing, right? So the instrument doesn't do any of this. So the instrument will produce this time series that's 16 kilo samples 16,000 times per second, and it looks more like this, right? It doesn't look this nice, but it's not windowed or anything. Then when you actually go and do the analysis you want to do, depending on what you're doing, you will do, if you are searching, for example, then you might grab some stretch of data, window it, Fourier transform it, and do that over and over again. If you're just analyzing a particular segment of data, let's say to extract the properties of 15/14, then you just do that for that one segment, and the sort of properties of this windowing will vary what you apply depending on what frequency content you're interested in studying and so on. So this is sort of in the post-processing stage, and it will vary from analysis to analysis depending on what you are trying to do. That makes sense. Yeah. To delta t. Yeah. So if you know that, okay, outside of the LIGO context, right? You know you want to capture some process in nature that has frequencies between 0 and some maximum frequency. Then you know that you have to sample that process at a frequency that is at least twice as high as that maximum frequency you want to resolve, right? We're not flexible in how much in the sampling frequency of LIGO, like 16 kilohertz, okay? So the issue comes in if you want to downsample that, right? So many times we're interested in signals that live at like 100 hertz. So we don't need to sample this thing at 16,000 times per second, because it's way higher resolution that we need. And it just makes your data processing very slow, right? Because you have, so then you want to downsample, right? So which one was it that worked, the orange one or the purple? Okay, well. So we start with something that's very fast, right? I don't know. But you're only interested in signals that evolve slowly, let's say, so you will only take points every so often, and then throw away the rest, okay? When you do this is called downsampling. It's sort of like picking a different sampling frequency, right, fs, and if you want to resolve, so then, let's see. So if you want to resolve a maximum frequency f max, then your sampling frequency should be f max equals 1/2 of this. So I said this backwards, but if you know you want f max, then you have to pick fs so that fs is twice the max frequency you want to resolve. Does that make sense? Okay. Well, we'll see applications of this later. Okay, so many times we're interested in not just taking the Fourier transform, but actually taking if you're working with data that's random in nature, then because it's noise, let's say, you want to estimate what the average Fourier transform is, and so over some long period of time. You can't just grab some data and do that because any given portion of data is just some random instantiation, it's some random draw from this distribution of noise. Okay, so you have some imperfect, you can't just compute the Fourier transform. That won't give you the full statistical properties of the noise, just an estimate. So to get a better estimate of the properties, you might want to grab your original set of data and split it up into chunks, and then analyze each of them and then average out. And so the random fluctuations in each draw will be averaged away. And we use this to compute what's called amplitude spectral densities of the noise, or power spectral densities, and it's just a nicer way of representing random data. And so what you do is, if you start with a chunk of data that goes from here to here, and you want to estimate what its Fourier properties are, so you split it into chunks that are some length represented by this red band, and we call that the FFT length, because we will take a Fourier transform over this much data, and then over this much data, and over this much data, after we have windowed properly to account for the boundary effects, and then we average all of these, and that will give us an average of the Fourier transform over this time. It assumes that the properties of the noise don't change with time, so it's stationary. So the properties of noise here should be the same as here, and so I can just average and get rid of these sampling fluctuations. Is this very confusing? Well, we'll see an example of this. For example, here. If I grab the data, I'm not sure. This should be the same data I showed you earlier, but I'm not 100% sure in the time domain, right? I can just grab the data, and I don't know anything, so I just take a Fourier transform. I get something that looks like this. On the x-axis, you have the frequency. On the y-axis, you have the Fourier transformed strain amplitude. We call this an amplitude spectral density because it will be, if you square it, it will give you the power in that frequency bin per hertz, right? So it has units of hertz, 1 over square root of hertz, because strain itself is dimensionless. So, okay, think about it. All right, so if you're not very careful, you'll get something that looks like this, and this is actually terrible. Okay, you have this feature, this sharp feature here that comes because you forgot to window your data, and this is characteristic of that. We can explain mathematically what disappears, but it's not actually in the noise. You know, you see this sharp drop here, and then you see there's a lot of variance, and it looks very messy. Among other features, you know, as I said, below 10 hertz, the data are meaningless in LIGO. Okay, essentially. So this is just random crap. So forget about it. And it only goes up to a few thousand hertz. Now, what you want to actually do to represent the power distribution of the noise in the Fourier domain is to do this averaging that I mentioned with the windowing built into it. So if you take so I think this was like 20 seconds that we started with or so, and then instead you divide it into 5-second chunks and average over them, and you take care of windowing properly, then you'll get this amplitude spectral density, which is it's a correct representation of what's going on in the instrument, not like all this stuff. I'll get to you in a second. So here you can see the sorts of noise floor that I mentioned yesterday from the instrument, coming from all these different sources of noise in the instrument. Well, you see this stuff again. This is to be ignored, and then this was produced with data from the Open Science Center that sampled at 4 kilohertz, and so there's a turnaround here at the maximum frequency of 2,000 hertz, which is where the max you can resolve, and then I'll come to this in a bit. Yeah. So far, there has been no assumption about Gaussianity or anything, but I'll come to that in a little bit. Just by looking at this, I don't think so. So you can tell some important features. You can tell that the noise is not white, which means it has different power at different frequencies. So white Gaussian noise means it has, like white light has components from all colors, so all frequencies. White noise has the same components at all frequencies. This clearly doesn't, right? We clearly have more noise at lower frequencies, for example, or higher frequencies than here. But this is in itself not, by eye, you can't tell whether the process is normally distributed or not. In the end, it will end up being because of the central limit theorem, mostly. I'll come back to that in a minute. I'm running out of time, yeah. I think it's just a way of making sure that the actual windowing process doesn't affect your final estimate, because some portion of data that here doesn't get included contribute too much to your Fourier transform. It does in the next one, and I think that's the easiest explanation. So in this way, you're making sure that you're not throwing away any information. And by the way, we don't do this manually, right? These are well-known data analysis methods, so you can, in Python, do Welch, and it does it for you. And I don't think we'll get to that today because I'm running out of time, but maybe it'll be your homework. Okay, so besides computing spectra, I can grab a day and then compute a power spectral or amplitude spectral density like this over the full day with some segment for producing the averages. I can also basically produce a plot like this, let's say every 1 second, or as a function of time, right? To try to quantify how the noise, this curve itself, will change as the instrument changes. So then you can represent that as a spectrogram. Okay, so in the x-axis you have time, in this case in minutes, and the y-axis you have frequency, and in color you have the amplitude of the Fourier transform, the amplitude spectral density. So the way you read this plot is if you imagine taking a vertical slice at any given time, that would give you a plot that looks like this. Okay, so the color, the color in this plot represents to the y-axis in this plot. And it's just a way of representing how the spectrum is changing as a function of time, if it's changing at all. So you'll see the same frequencies here, so there's high noise at low frequencies. You see here at low frequencies, it's very high noise. Then you have these spectral lines that stay coherent at the same frequency for a long time. That's what these lines are, right? These are features at a specific frequency that remain on. And then again, I mean, you see the variation in the overall noise floor in that it's getting brighter here and then goes back up. In this case, you don't see much variation over these 10 minutes. But if I was showing a day, you'll see that there's features that move up and down and as the instrument evolves. To pique your interest, here's a different plot of actual data around 150914. It's, 10 minutes around. It's centered at the time of 150914. And there's some there's an interesting feature in the spectrogram. Who sees it? That? Yeah, that's 150914. Okay. So this is what people mean when they say that if you look by eye, you can just see 150914 in the data because it was so loud. They mean that after you have taken the data and processed it properly, getting rid of all the frequencies, all the high frequency stuff, all the noisy high frequency stuff that is up here, and the noisy low frequency stuff down at lower frequencies that you don't see here. And if you remove some of the lines at 60 hertz, then you will just see 150914 appear in the data by eye. That's because the signal was very strong. It basically has no implication for the way we actually detect the signal. This is very important. We don't just go through the data and try to filter and see signals by eye. Okay, this is just neat. And it has so happened that the first signal was so loud that we can do this. So again, this plot is the same data as here, except that I've removed all the frequency content below. I haven't. Someone else made this plot, Duncan. Thank you, if you're watching. Okay, anyways. Below 50 hertz, we've thrown away everything below 50 hertz. We've thrown away everything about 250 hertz. And we've removed this 60 hertz line. And then that's what you get. And then this signal that has content in this band becomes apparent. Oh, okay, that's written there. Does that make sense, how this is obtained? Okay. Right. So I'm finally getting to what I wanted to get to. We have, 25 minutes, we'll see. So that's how a plot like this is produced. I showed a plot of this that represents the sensitivity of the instruments yesterday. And I explained how this curve sets the level of signals that we can detect. It represents our noise floor, so a signal that comes, if we want to detect it, should have power that lies significantly above this sensitivity level. And so you see we're speaking about 10 to the negative 23 in strain. This is already been calibrated and so on. You see this plot I've actually taken from a few days ago, because you can go online and see what our instruments are taking data right now. And we make available some summary statistics, including the sensitivity of the instruments over a given day. You have in red, you have the Hanford LIGO instrument. In blue, you have the Livingston LIGO instrument. In purple, you have Virgo. So you see Virgo is still doing a bit, it's less sensitive than the LIGO instruments. In black, it's not shown, but that's the German instrument, Geo, but it would be out of scale, I think, or it wasn't operating, but in any ways, it would be like way up here. So we don't actually use it. Yep. $70? This? Oh, sorry. This stuff. Yeah, I have no idea. Okay. I'm not sure if this is it. Yeah. I'm not sure if this is. Oh, yeah. This is. I do have an idea. This is. Oh well, I don't have the plot, but it has to do with how the suspensions are built, I think. So if you look at the ideal noise curve, I don't remember exactly where it is, but it has a bump here, and I don't remember what it is. I'll have to look it up. But it is by construction there, I'm pretty sure. Let me get back to you. I remember it was labeled in the plot I showed yesterday, but I forget. Okay, but I think it's supposed to be there. Does anyone else? Oh, Ricardo's not here. Maybe he. Anyways, the basic features of this curve are explained by physical processes that went over yesterday, like seismic noise, the coding thermal noise, violin modes, shot noise from the laser, and so on, that define the overall Gaussian noise floor of this spectrum. It's Gaussian again, just because all these sources of noise essentially we're averaging over it, so there's a central limit theorem, so they all contribute roughly to these Gaussian features. Then you have these coherent lines that again come from things like the modes from the threads from which the mirrors are hanging, the 60 Hertz line, and this that I don't remember what it is. This is still, there's other sources of technical noise that are elevated at lower frequencies that people don't know exactly where they come from, and so there's scientists working on these instruments. Well, right now they're observing, so they're not allowed to tinker with it, but during the observation, the periods where we're not observing, many scientists just work to lower this and clean it and understand it better. Okay, so you can go, well, I'll show you in the end how to actually see this for today, for example. Okay, so the resolution to which you can resolve spectral features is determined by the observation time. So this is computed over a day. So it means that if you remember your frequency resolution, your frequency bandwidth will be 1 over a day in seconds, okay? So you won't be able to see, to resolve lines. So if you have spectral features that are closer together than that, they will look like one big feature, like here. Here, what's going on is that you have many actual thinner spectral features that are now being resolved, and they look like this thing. If you integrate for, let's say, a year, then you will see that our data are plagued with these very thin, coherent lines that hang on for a long time. So instead of good things comes to those who wait, many lines comes to those who wait, because you start resolving this very long, very sometimes very weak spectral features. You can go, we have an online catalog of what these are. This is too small, but it says loss.ligo.org, spectral 01 spec lines for spectral lines. So this was for 01. You see, for example, this comb of lines at like 1 second, intervals of 1 hertz, and that has to do with the digital timing system. And these are were unfortunately coherent in all the instruments because they all use GPS time to keep time, basically. It talks to the GPS system, and there were LEDs that were blinking at 1 second, and that was somehow percolating and getting into the instrument. These were mitigated since once people discovered that, they fixed it. So I don't think they're there anymore. But anyways, I'm not sure. A lot of them are understood, not all of them. Yes. So besides new calibration, after the fact, some of these features are removed. For example, the calibration lines are removed because those we know perfectly because we put them in, so we can remove them coherently. The 60 Hertz lines we can to a large degree remove, and so on. It depends on whether you also have what's called a witness channel. So if you see this feature in one of the other 200,000 channels, so for example, something like the 60 Hertz line, you might see in sensors that measure magnetic fields or electromagnetic fields in the area. And so you can just correlate the actual gravitational wave channel and this auxiliary channel that's blind to gravitational waves and use that to subtract it and clean it. So when we produce clean data, a lot of this stuff is removed. I'm gonna say yes, but I don't know exactly. I don't know exactly which. I would guess those we have very good witnesses, so they're probably clean. If it matters. For some analysis, it doesn't matter. It depends what frequency you're looking at and so on. All right. So this kind of feature matters, again, when you're integrating and observing for a very long time, and you can actually resolve and become sensitive to these features. That matters if you're looking for pulsars, for example, or something where your actual signal should be there for a long time, and you have to integrate and observe for a very long time. And so these look very much like what a pulsar signal would look like, okay? Except the pulsar signal would be coherent so it would be in all the detectors, whereas these lines are not necessarily. so you want to clean that for those kinds of analysis or take that into account. But for analyses that look for compact binary coalescences, the main issue is not these long, narrow spectral features, but non-stationarity in the data, or what we call glitches. Every now and then, the instrument will just glitch. There will be some instrumental conditions that make the mirrors shake for some reason, or make it look like the mirrors are shaking for a very short time and with some particular frequency. So for example, this is an actual noise glitch in, what is it? Is it Hanford? I don't know what actual instrument was used here. So it's just H of t, and it looks fine, and all of a sudden, the mirrors shake with a burst of power, and then it goes back to what it was before. And you can visualize that with a spectrogram and see that you have basically just the Gaussian noise floor, and then all of a sudden this is like an instability in the system, and then it goes away. So these are bad because if you look for signals that are very short, I mean, it depends on what the morphology is, whether it would mess up your search or not. But you have to be aware. Yeah. Yeah, so there's many ways. So for many of these glitches, and there's a whole zoo of these features that show up again and again with similar properties. For many of them, there's a known coupling, so we see them, let's say, in the seismic detectors too. We know that that's not a gravitational wave, right? We have some witness channel that we can say, it's ringing up the gravitational wave channel, but it's also ringing up this microphone, or whatever it is that is itself blind, so we know it's not a gravitational wave. And many times, that way, we can trace back the origin of the noise and remove it. In other cases, we don't know what there's no other channel that sees anything. Like, for example, there's a class of glitches called blip glitches that we don't know where they come from so far. However, they don't occur in the different instruments either coincidentally or coherently. So they don't appear in the same instruments at the same time. So it can't be a real gravitational wave, right? So that's the whole key to searching for gravitational waves that you don't have a model for, is enforcing that the instrument sees something coherent that makes sense in all the instruments at the same time, whereas this noise is just independent to a large degree. So in the end, that's really the final bar. Anyway, so to understand all these things, we have in LIGO a whole set of people dedicated to assessing and improving data quality. These include the detector characterization group, and they determine which data are valid for scientific use and which aren't. That informs the improvement of the detectors. They can identify noise sources as these complicated machines evolve, and it's a constant hard work to actually understand these machines as they change and correct, and it requires a deep knowledge of all these systems, how they are coupled to each other, and how the information will show up in these 200,000 channels, and how it will percolate to the actual gravitational wave signal. And this is what I believe Florent's going to talk about, detector characterization, I don't know, next week, I guess. So I won't go into that. But one thing to keep in mind, I think it's fair to say that this process is becoming way more and more automated as time goes by. They have many tools to actually automatically identify correlations between the gravitational wave channel and auxiliary channels, and automatically say, okay, flag this as bad time to analyze, or so on. So you can be part of that and teach AI to recognize our glitches. You can go to gravityspy.org, and then it's based on Galaxy Zoo, for example, where astronomers use this crowdsourcing effort to categorize galaxies and their shapes. You can help us categorize glitches and their morphologies, and so to train our artificial intelligent overlords who will someday just run the instrument on their own, okay? And this is already being used. So the gravity spikes have been around for some time, and it's already to the point where it's actually informing what we do. So if you're curious, go there. I'm told it's fun. I've never done it. I don't know. Okay, so at the end of the day, if you're a data analyst downstream, what you want to know is what data is safe to use and what data isn't. And the way that the detector characterization people tell us that is by producing data quality vetoes. So they will say, look, at this time in the strain channel, you see this bump, but in reality, we know that that's correlated to some microphone picked that up, and there was some issue, I don't know, in the X arm. And so this is bad data that will confuse your analysis. Remove it or ignore. You should not analyze it for your data. And so this is an example here for specific glitches. Obviously it's a pictorial representation. And there could be localized features. So for example, there could be high wind activity and it causes something that looks like a gravitational wave, but it's not. And so these are what we call witness challenged. Important thing is they are blind to gravitational waves. There's no way that a gravitational wave itself would show up in any of these. So we know that we can safely throw away these data. When you go to analyze the data yourselves, when we get to that part, you'll see that this is part of the information we provide to you. There are several flags that at any given time tell you what the status, what the quality of those data are. Okay, so 0 just means we have data, so the instruments were on at that time. Then category 1, quality, so each of these, this is less conservative, and this is more conservative. So as you go from 0 to 1, you are demanding more quality, right? So if it fails a category 1 veto, so it's veto with category 1, means there's a critical issue, and you should not use those data at all. You won't have that option because we don't make data that are that bad available to you. So all the data that we make available publicly is at least category 1. It passes that first failsafe. Category 2 means there's some known coupling like this at some specific frequency, so you're still allowed to use it. For example, if you're only interested in frequencies that are very far away from where this stuff is happening, you should know that's there, but if you know it won't affect your analysis, you can still use it. Category 3 means there's some unknown coupling that we know not to be, we know it's not a gravitational wave, but we don't know exactly what it is. And so when you get the data, you can say how strict you want to be, and you want to analyze any data that we made available, or you only want to analyze data that we know, like, to a very high degree to be clean. And then there's some, that will be informed by the kind of analysis you're doing. Anyways, I'll give you, if we actually get at some point to working with real data, I'll show you how to use this. Anyways, so there are several components to our noise. We have mainly this Gaussian noise floor, but on top of that, and this assumed to be largely stationary, although it evolves slowly with time. But on top of that, we have these glitches that appear for a short time with some particular spectral shape. We have narrow, persistent spectral features, these lines. And there's another kind of noise that I didn't discuss that is broadband. So it appears at a large, presumably appears at a large band of frequencies and is around for some time. And it actually appears in all instruments around the world, and it has to do with Schumann resonances, which are resonances in the electromagnetic field of the Earth, resonances in the atmosphere between the surface and the ionosphere. So whenever there's lightning somewhere, there's this electromagnetic oscillations around the world, and they show up in all the detectors, and they matter if you want to analyze in search for example, the stochastic background. Anyways, there's a lot of efforts to understand, characterize, and mitigate all these noise sources. In the end, the final way that we really know these are no gravitational waves and it's noise is that they will appear in one detector and not the other at the same time or in a meaningful way. And that's one of the main reasons why having more than one detector is paramount to detecting signals at all in the first place, right? We could have never claimed a detection with just a single interferometer. No one would have believed it, and they shouldn't. Okay. All right, I have less than 10 minutes. Maybe I'll fly through this, and if you get bored, if you don't understand, I'll come back to it at the beginning tomorrow. So when we, as we'll see after the search is done and we want to analyze, extract the properties of a gravitational wave, we will assume that all this vetoing and cleaning has been done, and that our data, the noise in the data is largely Gaussian, plus possibly a gravitational wave in there. But forget about the signal. So now, what are you need to understand what the properties of Gaussian noise are. Okay, so a bit of fun to me, statistics, okay. So what are the properties of Gaussian noise? Well, if you just draw some some single variable that usually we call it x, but here I'll call it ni, from a Gaussian distribution that has 0 mean and some standard deviation sigma, the probability of drawing any given value will be given by this exponential e to the minus ni squared over 2 sigma squared. Okay, this is just saying that the farther it is away from 0, the less likely it is, with some characteristic scale set by sigma. Okay. When we have multiple samples, so let's say I have a time series of random noise that I've sampled from, for example, LIGO, that will be described by a multivariate Gaussian or normal distribution, because each time sample is actually a random variable associated to the same underlying random process. So if you like statistics, then you know what that means. If you don't, it doesn't matter. What you need to know if I have a series of time samples that are known to be Gaussian noise, then that whole set of big N samples will, so the probability of drawing that from a multivariate Gaussian distribution is very, very similar to the one-dimensional case. Is e to the minus 1/2 the product of the values, but it's the inner product of the vectors weighted by this covariance matrix. Does this make sense? So another way of writing this without indices is just, you have a noise vector that's made up of all the samples that you measured, and you have some matrix C that is a covariance matrix. You take the inverse, and then you sandwich it with your noise vector. Okay. The covariance matrix is just the multivariate generalization of the variance, right? So it just tells you the diagonal components are just the variance in each of the random variables. The off-diagonal components tell you how correlated the different variables are to each other. Okay. Is this like totally foreign to any of you? All right, this is what defines a Gaussian process, that we can write a probability function for it that has this form. All right, so this encodes correlations between the different samples. This is important. This means that so when we have a series of noise samples, they are not uncorrelated from each other necessarily, and they will not be in the case of LIGO. And that's just because if you have noise at higher frequencies, if there are, for example, some frequencies of which you have more noise than others, you're more likely to see those frequencies appear, and the samples will be correlated by the fact that you have noise that has more amplitude at a given frequency. Anyways, so we don't need to. We should not assume that the samples are uncorrelated. Otherwise, if they were, this covariance matrix would be diagonal. Okay, so you just would have a bunch of these sigmas in the diagonal, but that's not the case. What you can assume, and we assume for LIGO data analysis in general, when we're analyzing a short amount of data, is that the process is stationary, which means that it doesn't matter when the data are taken. It just matters how far away the 2 points are to each other. Right, so if you take points that are very close together, they might be more correlated than if they're far apart, for example. or it might depend on the period of that separation and so on. So this covariance matrix will just depend on the difference. So here I and j index time samples. So this is just the correlation length, the separation between them. There's a sampling theorem. There's a theorem in statistics, the Wiener-Kirchner theorem, that tells you that if you have a process like this and this function is continuous, then in the Fourier domain, the equivalence covariance matrix that relates the Fourier components, the Fourier version of those amplitudes, is you can write as 1/2 some function s of f, because now we're in the frequency domain instead of time domain, so these are not indexing frequencies, delta ij. So this is diagonal in frequency. Okay, so let me rephrase it. You grab a stationary Gaussian process, the samples are not necessarily uncorrelated, so you have a covariance matrix that is not diagonal, it has components all over the place. However, if it's stationary, you know that if you Fourier transform the data, the covariance matrix of the Fourier amplitudes will be diagonal, okay? And the values of that diagonal will be the power spectral density, which is the square of the amplitude spectral density, which is the quantity that I've discussed earlier. The amplitude spectral density, remember, is the spectrum I showed you before. So that's why I made an emphasis on how we compute with Welch method and so on, because that's what determines the statistical properties of the Gaussian noise floor. So in other words, the problem diagonalizes in the Fourier domain, so then we can, if we are now talking about Fourier amplitudes, so not n, but n tilde, that means Fourier transformed, right? So now the indices in index frequency bins, you still have n of them, but it's in frequency, not time. Then the likelihood is just a sum. So it's the same form as before, like this, except it's like Cij is diagonal, so you only have to worry about samples, the norm of the complex amplitude divided by the PSD, and this is just to get the units right, and you sum over the whole data. You can look at this and be inspired and say, well, this just looks like a dot product between the two noise vectors, except I have this measure, this weight by the PSD. Okay, I'll come back to this tomorrow in more detail because I ran out of time. But this will be a fundamental quantity in data analysis. It's the inner product of two data vectors. It's in the continuum limit, just an integral over frequency weighted by the power spectral density. Effectively, if you look at this, you'll see that you're assigning more weight to areas of the frequency space in which S is lower, which means you have better sensitivity, whereas you are downweighting areas in frequency that have very high PSD. So this defines a norm. It's a normed inner product. All right, I'm gonna start with this tomorrow because I'm out of time. All right.
If you can show that spectrogram again, I believe there was kind of an artifact, dashed line.
This, or what?
No, the overtime. These overtime.
Oh, the spectrogram. Yeah.
Yes.
This one, or which one, or this one? Or this one?
Yes, this
right.
one. There's it seems a dashed line.
This.
Yes.
Yeah.
What is this?
I guess that's, I don't know. That's a line